In this lecture, we will cover design methodology. First, an important definition. Design engineering is the development of a product, system, or production process that meets the customer's needs. Easy to say, hard to do. You'll find thousands of job openings nationally on the job sites for this discipline. Maybe you'll get a job in this field after graduation. Product design has an endless number of possible solutions to a customer's problem, as defined by the marketing requirements. It is not an analytical class like fluid mechanics or heat transfer with only one correct answer. You'll need to get used to the ambiguity of design. There are good designs, bad designs, very good designs, truly lousy designs, awesome designs, terrible designs, and so forth. A design is ultimately judged by the customer for the product, not by the product designer. Design success takes on many forms: happy customers, writing good reviews on the web, big profits for companies, praise, glory, and big raises for the product designers. Design failure, is ugly. Customers torching the product in their online reviews, companies losing big money, and product liability lawsuits in rare cases when customers are injured by a product. Just ask the automobile companies about that. Let's go over a second important definition. Total design is the systematic activity of people, processes, and tools that creates a product to satisfy the user need. There is a subtle difference between design engineering and total design. Design engineering involves the development of a product, something tangible. Total design involves the methods you use for creating a product. In other words, a system. In total design, you ask about the commercial viability of a product, your team's ability to complete the design, and the level of risk involved. You need to answer yes to these questions. Does the product meet the customer's unmet needs? Note that our market research uncovers the unmet needs. In total design, we ensure that the product design satisfies the unmet needs. Do we have sufficient technical experience to get this job done? For this class, that means team members having taken the proper courses in ME or EE to do the design work needed. Does the design satisfy the market requirements in PDS? You will wrestle with this question when you create your first concept sketches a couple of months into the semester. Do we understand the technical risks? For this class, that means assessing if you can get a working prototype built by next May. If the technical prototype is of too high level for your team, you'll never finish in time. So make sure you select a project commensurate with your own level of education and experience. Does our design infringe other firms' patents? I will give you a quick lesson in an upcoming video of how to search for a patent on the U.S. patent website, how to read the patent claim, and how to assess if your idea for a design infringes a patent. This slide shows the major activities of total design, which you will follow in this class. The conceptual design phase involves generating multiple system-wide solutions to meet the PDS. This is followed by detailed design, which focuses on designing the subsystems and components. The details are documented in component part drawings, schematics, and software. Based on the detailed documents, you purchase components or build them in the shop. You then assemble the parts into a prototype and test the prototype as proof of concept. The Lamborghini is an example of excellent total design. It's beautiful to look at and everyone wants to drive one. Only its exorbitant price prevents that from happening. Partial design is a subset of total design, either a subassembly or subsystem of a product. You've all been taking engineering courses in partial design for the last couple of years. They're taught as core courses in the mechanical, electrical, and chemical engineering disciplines. They include fluid mechanics, thermodynamics, heat transfer, vibrations, and my favorite, machine design. You integrate all the partial designs in order to build a complete product. Different combinations of partial designs give you different models of the same product family. But you must be careful not to focus exclusively on one partial design and hurt the others when you integrate them in a product. This slide shows the partial designs of a gasoline-powered automobile, depicted as major systems in this diagram. The engine is the heart of the car. Machine parts design and thermodynamic analysis are the major skills engineers need to design the engine. Moving counterclockwise around the frame, you see the radiator system, which keeps the engine at operating temperature. Schooling in sheet metal design and heat transfer gives the partial design skills you need to design the radiator. To design the frame, you need to know sheet metal design as well as stress analysis using FEA software. For the tires, you need to know how to design rubber parts, and skill in pneumatics is needed too. To design the seats, you need to know about design of molded parts, in this case with recycled plastic fibers. You need to work both systematically and logically when doing product design work. First off, don't cut corners and go one step at a time. Don't start conceptual design until your PDS is fully written and approved by your team. It's likely that your early design concepts will deviate significantly from the PDS. Resolve the discrepancies early in the conceptual design phase. Check dimensions carefully and make sure that all parts will fit together properly before you assemble them. If the prototype does not work correctly, stop and correct the part designs as needed. Lastly, make sure the dimensions you pick for components are based on analysis, whether thermal, stress, vibration, fluid, or machine design. You've taken all these classes. Now use what you learned.